We're back for more for the exam review for AP Physics 2. We've been dealing with the electrostatic issues, so just kind of help us remember how to do all this. So what do we have here? An alpha particle is approaching a golden nucleus, like the Rutherford experiment. It's got an initial velocity of 42,000 meters per second. From this position here, what would be the acceleration, the magnitude of the acceleration of this particle? Of course, we know that these two are both positive in charge, so they would actually, this thing would be accelerating in that direction. So I'm just going to set force electric equal to ma. The net force acting on this object would equal just the electric force. So then I have k q1 q2 over r squared equals ma. Okay, now the charge on this will be twice that of an electron. This will be 79 times that of an electron, because that's the atomic number for both of those. And of course, the mass of this would be the mass of this particle here, which is alpha particle, which is a helium nucleus, and that would be 6.6 times 10 to the minus 27 kilograms. Now, what if I wanted to know how close could this particle get to this gold nucleus before coming to a complete stop? So again, we're going to keep coming closer and closer and closer, and this gold is going to keep pushing farther and farther this way. So what's going to happen here is the kinetic energy of this particle will convert itself to electric potential energy. So when it comes to complete stop, it'll all be electric potential energy. Now, of course, it'll go backwards after that. So it's going to be 1/2 mv squared equals k q1 q2 divided by r. Now remember, the q would be twice electron for this, 79 times electron for that, and the mass for this is 6.6 times 10 to the minus 27 kilograms. The r you're calculating here will be equal to the distance from the center of this atom, the closest that it can approach to it. All right, next one. What about the Robert Millikan experiment? Well, we are going to suspend an oil drop in midair here. So we'll have force gravity downwards, and of course force electric upwards. And these two will be equal to each other if that's suspended there. And this particle is going to be a slight negative charge, and it's our job to figure out how many extra electrons are on that. Of course, this will be our positive plate. This is our negative plate. We adjust the voltage until this thing is suspended. So our first step is use the Vetch equation in order to get electric field. Electric field between the plate. So electric field then is equal to force electric over charge. We really want to find charge. Once we know electric field, we can know force electric because force electric is equal to mg for this particle here. So electric field then is mg divided by q. And now we can solve q by taking mg divided by electric field. And once we find q, okay, we can divide that by 1.6 times 10 to the minus 19, and that's going to equal your number of electrons extra on this. And that's how you do the well drop experiment from Robert Millikan. The key really is understanding that force electric and force gravity equal each other, so that you can use the base equation for electric field as force electric per charge. And that's how that's done. Okay, next, what if I have 3 charges in a triangle shape here? And of course, that looks like an equilateral triangle everywhere. It's our job to find the value of the voltage at this location here. Remember, you'll have to use just a little bit of trigonometry or Pythagorean theorem. You can calculate the distance between these two particles. And then I'm just going to do, let's call this one 1, this one 2, and this one 3. So I'm just going to summarize the volts of 1 plus the volts of 2 plus the volts of 3. Now remember, this one's a negative, so essentially that's going to be a negative 1. And then what am I going to do? For each voltage, I'm just going to say volts equals kq divided by r, where the q is the value of each charge, and r is a distance from x to each of those charges. So it's just a matter of adding up, and that's going to be equal to voltage total, or potential total. Remember, voltage is not a vector, so we don't need to do any x's and y's for that. So that's pretty easy to do. Okay, what about finding the capacitance for a capacitor? Well, if I've got two parallel plates here, of course, there'll be some voltage source attached to it. We don't need to know that because all we want to know is the capacitance value here. So the equation is capacitance is equal to epsilon naught A divided by D. Okay, A, of course, is the area of the plates. D is the distance between the plates, whatever you want that to be. And epsilon naught is the permittivity of free space, which is 8.85 times 10 to the minus 12. So it's just a plug and chug equation. We find the capacitance value, and it will be in some kind of farad value when we're done. Now, what if I insert a material in between these two plates? Well, then there will be a dielectric constant K, and that'll equal some value. And all you do then is multiply your answer from this by whatever this K value is. Often we insert the K right here in our equation there. If there is no material there, we just put a number 1 in there to represent the value for the dielectric constant of air. So that's a very easy equation to do too. Okay, and lastly, what about our capacitors in series parallel combination? Okay, well, if I've got 12 volts, we know that 12 volts is going to go across this branch here in total. And of course, 12 volts will cross here because that's the parallel part. So if I want to know the charge and voltage on any of these capacitors, let's just look at the top branch here. Okay, for this, and I'll actually do this. So I'm going to take 1 over C total equals 1 over 100 plus 1 over 220. And of course, then I'll get some kind of a C total value. Okay, well then I can get the charge on these guys by saying Q is equal to C total, okay, times the voltage. In this case, the voltage would be 12. So I'll take C total times that 12, and then that will be the charge on both of these capacitors. So I'll just label those as Q because they're in series with each other. So the charge on both of them would be the same. So then how would I get the voltage on either of these guys? Well, the volts is going to equal charge divided by capacitance. So I know the charge on each of these. I can just divide by the capacitor's values, and I'll get volts. And I'll do likewise on this one on the bottom here. They'll be identical, except, of course, different values. And that's our review for the test for electrostatic portion. And we'll look forward to doing more videos later.